Good afternoon, everyone. Today, my name is Ray Ding, and today my talk is about a novel logging mechanism, which is named Log2. Log2 is a cost-aware logging mechanism for performance diagnosis. So the performance logging is very common nowadays. For example, for one online service system in Microsoft, about 20% to 40% of the total logs are performance logs. The performance logs usually consists of two performance logging API, a pair of begin and end functions. These two functions monitor the code region and mainly calculate the execution time of this monitor code region. When these performance logs are generated, these logs are very useful for diagnosing performance issues as well as understanding the system states. However, the logging comes at a cost. So considering that the operating the logs, transmitting and storing the logs, so the additional overheads are needed, such as the CPU usage and I/O bandwidth. So since the logging needs overhead, so it has the potential to impact the normal service execution. For example, when the logging is fully conducted, the latency will increase about 16%, and the average throughput will decrease about 1.5% for a search engine. And another issue is that huge volume of logs could cause long log processing time and make the burden log analysis, since the useful logs are usually hidden among huge number of the other irrelevant logs. To comprehensively understand the logging cost in practice, we conducted a survey and received feedback from 82 logging experts in Microsoft. According to the feedback, 80% of the respondents agreed that the logging cost is a non-negligible issue, and about 60% of these respondents experienced the negative consequences of the heavy logging cost. For example, in the table below are several real cases of these negative consequences caused by the logging cost. For example, about 58% of these people complain that the I/O bandwidth of logging may be an issue, and sometimes it will cause the perception of interference with the core normal service functionality. We further asked the respondents, what are the most common solutions to control logging cost? And according to the feedback, the most common three solutions are listed on the right-hand side. They are adjusting the logging level, removing unnecessary logs in source code, or archiving local log files periodically. However, these solutions are not perfect. For example, since they cause either significant manual efforts or heavy system operations. For example, removing the logging statements in the source code needs recompile the source code and do some testing, and at last need to redeploy of the service. In addition, according to the feedback, more than half of the respondents agreed that they are not satisfied with these current solutions. We summarize one interesting and important observation from this survey. So most people agreed that the useful logs are only a few. About 83% of the people replied that many log messages are not useful for the issue under investigation, which indicates that eliminating these logs has little loss on effectiveness. Then, considering the serious cost produced by logging, which implies that a solution on reducing logging cost while preserving the effectiveness is feasible and, of course, is well motivated. To address these issues caused by the logging cost, we propose our approach, which named Log2. The specific problem is defined as follows. Given a predefined budget on I/O bandwidth, we aim to provide a lightweight logging mechanism to dynamically eliminate irrelevant logs such that the preserved logs satisfy the following two properties. The first is budget compliant. The second is the saved logs are still effective for performance diagnosis. Designing such a logging mechanism is non-trivial. Three major challenges are encountered. First, retaining budget compliant while preserving logging effectiveness is non-trivial. We can imagine that writing fewer logs would certainly reduce the logging cost. However, apparently some useful logs will be missed. On the other hand, writing too many logs would preserve the effectiveness but introduce significant logging cost. Therefore, making an optimal balance between the logging cost and the logging effectiveness is a challenge. And the second challenge is that the additional overhead incurred by the log square itself must be low so that it wouldn't impact the normal service execution. Furthermore, these above two challenges becomes even harder due to the system dynamics. The system dynamics, such as the workload changes, the configuration changes, are very common. In practice, so a pre-set up static solution cannot work well under various types of workloads or configuration settings. Therefore, our approach should be self-adaptive to these system changes. In order to address these challenges, we designed the log square. This is the overview of our approach. Briefly speaking, log square answers one important research question: whether to log. That is, given logging request under investigation, log square decides whether or not this log is dumped or discarded. More specifically, log square makes the whether to log decision through a two-phase filtering mechanism. The first phase is called a local filter, which is executed within each performance API. In this local filter, a large number of the relevant logs are discarded efficiently. The second phase is called a global filter, which is triggered periodically on a global memory cache. In the global filter, useful logs are cached and output while complying with the logging budget. Before we drill down to the details of the two filters, let's look at two brief examples for preliminary understanding. The first one is an example of the local filter. Now, suppose we saw the execution time of a function foo is about 55 milliseconds. And I know that normally this function is executed within about 20 to 100 milliseconds. Then this log looks normal. So it is not necessary to be dumped to disk. So this log is discarded. Below is an example for the global filter. So after a period of time interval, the global filter is triggered. Now, the cache of the logs are 600 kilobytes. And we know that the budget is 500 kilobytes. So we need to identify the best 500 kilobytes among these cached logs and dump them to disk. And at the last, I also need to notify each local filter to increase the bar of this log discarding, since the cached log size has significantly exceeded the budget size. These are two brief examples. So here is the detailed illustration of the local filter. In the local filter, a utility score is calculated for each logging request to represent its usefulness for performance diagnosis. Considering the nature of diagnosing performance issues, two key information are taken into account: the current execution time of a specific function and its histogram. Once the utility score is calculated, the log elimination is conducted by comparing this utility score with the global threshold. So if the utility score is smaller than the threshold, it will be discussed directly. Otherwise, it will be cached, inserted to a global buffer. Defining a proper utility score is very key to the success of local filter. So as stated just now, one essential information for performance diagnosis is the histogram of the execution time for each individual function, which represents its normal behavior. So we adopt the method of moments from the statistical literature to approximate this histogram. Such method only needs the constant memory usage to store the estimated moments. In order to tackle the slow varying system states, it is not proper to estimate the moments with all historical data under equal weights. Therefore, so exponential smoothing is adopted. And a further benefit of the method of moments is that the moments can be updated incrementally. So the updating time is with time complexity O1, which minimize the computational cost incurred by the local filter. Last but not least, in order to fit to the different scenarios, we provide configurable definition of the utility scores so that users can conduct tuning to choose his best utility score to fit into his specific scenario. Next, let me illustrate the details of global filter. Global filter is triggered periodically, which mainly consists of two tasks. The first task is to dump the logs which with the highest utility scores and also assure the budget is compliant. The second task is to update the global threshold and notifying the local filters of such updating. The goal of the threshold adjustment aims to make the cache size of the logs approximately equals to the budget in the next interval. So it is basically a prediction problem. Adjust the global threshold is the key to the success of global filter. First, the memory usage of the cache needs to be controlled to assure the low resource usage of log square. Therefore, the threshold of adjustment should let more logs discarded when memory usage increases. Second, the threshold adjustment should be agile to the workload changes, since the workload changes is very common in the real systems. We adopt the techniques from the reinforcement learning literature to address it. Basically, we learn and guess a best threshold from the history, and while both the threshold and history data are updated continuously. Third, of course, the updating, the complexity of the computation of updating must be very low, so it is also with time complexity of 1. Last but not least, we also support the budget change on the fly, which enables developers to tune a proper budget for his specific environment and his specific requirement. To demonstrate the effectiveness of log square, we conducted evaluations on two systems. One is an open source web application named BlogEngine. The other one is one online service system in Microsoft, which is named ServiceX. We evaluate the log square from 3 key metrics. The first is login throughput. So we compare the login throughput of the log square with the existing login system. The second is the logging effectiveness. So by varying different budget size, we would like to see the effectiveness, how much effective can log square be preserved since it has compromised the logging cost. At last, the third metric is additional overhead. So the additional CPU and memory usage of the log square itself must be very low. This is the evaluation setup of BlogEngine, and we first conducted the instrumentation to more than 1,000 individual monitored code regions, and according to the guidelines inspired by several previous papers. And in order to evaluate the logging effectiveness, we do some performance issue injection. So we take this injected performance issue as the ground truth, and we see how many of these injected performance issues are covered by the logs stored by the log square. And we use about 100 synthetic users to concurrently access to this BlogEngine, and we do the experiment for several rounds to overcome the random variation. And this is the evaluation results on I/O throughput. The blue curve is the actual I/O throughput of the traditional logging system, so which is the default logging system used by the BlogEngine. So it is very straightforward that once the login statement is executed, it will be dumped eventually to the disk. And the red curve is the I/O throughput of log square once we set the budget to 120 logs per each time interval. So we can see that the average I/O throughput reduction of logging is more than 97%. And so the previous slide shows the I/O throughput. So this slide shows the effectiveness. They are quite associated with each other. So here are three curves. They are three different definitions of utility score. And we can see that the coverage goes increased to very close to 100% when the budget size reaching to about 100 logs per interval. So what does this mean for 100 logs per interval, which is approximate about 2.5% of the sampling rate? So actually, this is a very low sampling rate. But the coverage of these performance issues has already increased to close to 100%. And this slide shows the results on the additional overhead. So we can see that for the memory usage, log square has no noticeable additional memory usage compared to the traditional logging system. And note that for the CPU usage, log square seems slightly lower than the traditional logging system. One possible reason is that since many of the logs are discarded before processing them and dumping them, so quite a few of the CPU usage for processing these logs are saved. So which may be the reason that the CPU usage is reduced. We also conducted evaluation on the real logs generated from one service in Microsoft. So we randomly selected about 12 log files. Each log file is about 500 megabytes. And since these logs do not have the ground truth, so for this evaluation, we designed to identify the performance hotspots. So we define the logs which the 0.3% of the logs which took the longest execution time as the performance spots, and we would like to see if the log square can capture them by varying the different budget size. So below, in the evaluation results, we can see that the coverage quickly reaching to 100% with a really small budget size. So for example, so we can reach about 98% of coverage with only less than 1% of the sampling rate. The foundation of that make log square enables log square to make sense is because that indeed among the huge volume of logs, most of these logs are not irrelevant to the issue under investigation. So log square is the first step to open the new to enable many directions for the future research work, such as for example, so we can enable the budget control for multiple services. So currently, log square is designed for one service and associated with this corresponding logging system. So if one physical machine has several services, we can build up a upper level layer to reallocate the budget for each service, and which may be more reasonable for machines I/O throughput. Okay, so in summary, we propose a cost-aware logging mechanism, log square, which makes the optimal whether to log decision. It selectively records useful logs. It complies with the budget definition, pre-specified budget, and it self-adapts to the system changes. And our experimental results show that log square can control logging overhead while preserving logging effectiveness. Okay, thanks. So.
Questions?
So yeah, one question. So how is your technique different from anomaly detection? As far as I understand, like, so your local filter is like an anomaly detector that you only log the a normal readings.
Okay, so for performance diagnosis, the practice mostly similar to anomaly detection. So I would like to see a specific execution time which is abnormal compared to this normal to the most of the time. So this is right. So this is about how to design utility score. So I have several examples in the previous slides that. So the utility is defined just as the anomaly. Okay. Yes.
Follow-up question. So you have to remember what's the normal,
Yes.
execution time is.
Yes.
Okay.
Mm-hmm.
Thank you.
I have actually two questions. So one is, so it looks like this talk focused on performance bugs.
Yes.
Have you tried to apply your system to like correctness bugs?
This is a very good question. So the key difference of performance bugs compared with other bugs, such as functionality bug, crash bugs, is that the performance bugs is relatively simple to calculate its utility score. So it's execution time, the histogram is execution time. But for the crash or the functionality bugs, it's usually associated with the contextual information, which is not an isolated which cannot be simply solved by the isolated information itself. So this is it's a challenge and one of our future work.
My second question is, looks like in the paper you described the API, like the log square begin and end. You actually log the actual timestamps of the events. So are they physical timestamps, like physical clocks, or are they like logical clocks? Because assuming you're applying this to a large distributed systems with multiple nodes, and their clocks may not be precisely synchronized.
So yes, for this, so they provide, so this service provide the performance APIs. So they use, I think they use the date time, so something like that to record the execution time.
I assuming like in your system it doesn't matter because you just calculate the time difference.
Yes, the time difference is the key.
Thank you. Let's thank the speaker.
Thanks.